Good afternoon, everyone. Thank you for joining us. I hope you're keeping well wherever you are and that you haven't fallen victim to COVID, or at least are only suffering the COVID restrictions rather than actual COVID itself. I'd like to thank the National University of Ireland Galway for hosting this event today, in particular Dr. William Finnegan and his colleagues for organising this webinar. I'd like to thank our presenters also for arranging to be with us and developing their presentations. The motivation for this webinar is that we have a coincidence of both several EU projects drawing to a close, and in particular the Leapwind project, and the researchers within that project wish to present their results. We also have several projects that SEAI has funded that are in their startup phase this year. So I suppose my objective was under the Irish Wind Energy Research Network was to bring these projects together to exploit synergies and to see what potential new collaborations could grow between these projects and potentially with other researchers also. The first session in this webinar will be presentations from those that have been involved with the Leapwind project, which was led by Air Composites and the National University of Ireland. And then the second session will be presentations on other projects, the projects that are have been funded by SEAI and that are in their startup phase of their research. And also Dr. Paul Leahy from University College Cork will be presenting on the EU Rewind project on sustainable decommissioned composites materials from blades. Certainly blades are very topical at the moment. IEA Wind has started 2 new research tasks on wind turbine blades, one on the erosion of wind turbine blades and the other on recycling of wind turbine blades. And certainly we have an active interest from participants in Ireland in participating in those projects, and indeed some of the projects that SEAI has funded can contribute constructively to those international collaborations. So the other aspect I suppose I'd like to emphasize is that there's quite a spread of research across different research organizations or research institutes in Ireland on wind turbine blades, and certainly that's gratifying to see that we're getting an organic growth of research on a specific area of wind energy technology. And certainly it's been my objective in setting up the Irish Wind Energy Research Network to stimulate both that base of wind energy research in Ireland, and also to make sure that we get collaboration between the projects and exploit whatever synergies there are. So I'll hand over to William Finnegan, and again thank you William for hosting this, and also thank you for joining us today, and I hope you enjoy it.
Thanks, John. Just 1 second. Okay, thanks, John. To start off today, I'm kind of introducing the next 3 presentations. So within the Leapwind project, it was a collaboration between Air Composites, who were the lead, Suzlon Energy Blades, and NUI Galway. So the Leapwind project aimed to develop a solution for leading edge erosion in wind turbine blades. Within the presentation today, I'll go through the main challenges and motivations, which is a general introduction to today's seminar, then go on to some of the testing we did to de-risk the solution that we had derived, including full-scale structural testing on a 13-metre wind turbine blade and operational trials that have begun in Scotland. Then I'll give an overview of the project in general. So the main motivation for this research is the occurrence of leading edge erosion on wind turbine blades. As the industry grows, wind turbines are getting larger and larger, and tip speeds are increasing, where they're reaching over 300 kilometers per hour. Due to these high speeds and the presence of moisture in the air, rain erosion is occurring along the leading edge of the blade. With no protection in place, this will occur well within 5 years of operation. But even with a protective measure in place, maintenance needs to occur quite regularly, which in turn is a costly affair. While this is rather straightforward onshore, as we move offshore, it becomes a more challenging and more expensive issue. It also has a knockback effect on the energy production of the blades, where it's been reported there can be a reduction in the annual energy production of between 2 and 25%. This can be quite, when you're dealing with small margins as operators are in the industry, this can have a significant effect on your business. So what we propose is to eliminate this problem in the design and manufacturing stage by introducing an advanced thermoplastic material along the leading edge of a wind turbine blade. So the first stage of development was to take all the candidate materials and perform rain erosion testing, which was completed at the University of Limerick, where Dr. Mark Hardiman will talk more about their rain erosion facility later in the day. We selected a thermoplastic solution, and the first kind of de-risking we performed on it was to create a leading edge demonstrator from glass fiber reinforced epoxy and bond this thermoplastic solution to the leading edge. We then, shown here on the right, undergoing a 4-point bending test, and this showed to be in line with what we predicted from our models, which is published in Wind Energy Science. The next stage of de-risking was to install the solution on a 13-metre wind turbine blade and undergo structural testing at NUI Galway. You can see here a multi-actuator system in place to test the blade, where the distributed wind loading is dispersed over the length of the blade at 3 locations, and 3 actuators apply a force at these locations. The first part of testing was performed static testing, where we recorded the displacement along the length of the blade and the maximum strains along the spar caps. The next stage then was to look at fatigue testing. So hope this video is working. We performed fatigue testing on the blade to see how the new protective coat would last over an operational lifespan of the blade. So we can see here a close-up of the thermoplastic solution that's bonded to the leading edge, and in order to monitor its performance over the fatigue test, we installed some strain gauges. We found that the strain on the LEP, or the thermoplastic solution, was much less than the blade substrate adjacent to it. The only damage that we did see was at the load introduction points, and this is kind of false damage introduced by a point load that wouldn't normally occur in operation. The results from this testing have been submitted for publication in the Journal of Structural Integrity and Maintenance. Once we de-risked the solution at this level, the next stage was to move on to operational trials. These have just begun and will continue for 6 to 12 months, depending on how they're going, essentially. So the solution was installed on a thermoplastic polypropylene small wind blade, and that's been deployed in Shetland, Scotland. This will be monitored continuously with visual inspections occurring monthly at the site in Scotland. On each turbine there was 3 wind blades installed, one with no coating, one with commercially available coating, and one with our LEP solution. And we will compare these over the duration of the operational trials. So in summary, the main objective of this project was to develop a novel solution to protect against leading edge erosion in offshore wind turbine blades. It was funded under the Executive Agency for SMEs in the European Commission through the Leapwind project, and it's a collaboration between NUI Galway, Air Composites, NAC Blades. The main objective was to design and manufacture this new component, and it was de-risked through rain erosion testing, large-scale structural testing, and now operational trials. The main impacts will be a new product for Air Composites, a lowering of the cost of wind energy for the industry, as maintenance will be avoided, which will become particularly expensive as we move offshore. And finally, job creation in a rural area, such as Connemara, where Air Composites is located. So thank you very much, and I'm happy to answer any questions you have in the Q&A session.
Thank you, Tomas, and I'd emphasize to the audience that if you have a question, to type it into the Q&A on the webinar platform, and we'll address those at the end of the session. We have a change to our running order. We've had a couple of presenters having IT difficulties. So Jamie Goggins of the National University of Ireland Galway will now present on the large structural testing of wind and tidal turbine blades.
Okay. Can you hear me there okay?
Yes, yeah. You're fine, Jamie.
Yes.
Yeah. Okay, very good. Thank you very much. Okay, so just follow on from Dr. Finnegan's presentation in terms of that some of the testing that he discussed there would have happened within our laboratory, the Large Structures Test Laboratory at the National University of Ireland in Galway. So I'm going to just talk about some of the work that we've done in terms of structural testing of wind and tidal turbine blades. So we're based at the National University of Ireland, but we're part of the National MaREI Centre. So that's the Centre for Energy, Climate and Marine. It's an SFI funded centre, but there's lots of other funders as well that fund our work. Okay, so we do things, blades for wind and tidal, but also we do other structures as well, like for the space industry, for buildings, for earthquake, for structures stay off with earthquakes, and we also look at sustainable processes, in particular life cycle assessment of various different structures. In terms of the wind and tidal turbine blades, we work across the area. So our main, I suppose, focus is in terms of testing blades, testing rotor blades over on the right hand side. So our lab and the Large Structures Test Cell within our lab is available to developers and researchers across Europe and actually beyond, underneath the MaREI 2 programme, which is the Horizon 2020 programme that gives free access to developers. We also have collaborate with various different companies and research organisations in relation to design and development of blades. So we developed our own in-house software called BladeComp, which can quickly create a blade, and we also have an optimization functionality or tool built in there into it so that we can get an optimum blade fairly quickly. Obviously, we need to understand a bit about the composite materials And we've done various different work on that, and we collaborate with various different people in terms of on the composite material side. So a little bit more about our test facility. It's a large structures test cell. We've got 4 hydraulic actuators currently in it, a strong floor and a test frame that can be easily changed around. On the image there on the right hand side, that's a 13-meter wind blade that's in there, and that's actually Dr. William Finnegan in the very background. You could see him there in the background of it to kind of give an idea of the scale. We've also got a lot of other test facilities within the lab as well. We have a data acquisition system that can read up to 120 channels simultaneously, and some other advanced instrumentation like digital image correlation, 3D laser scanning, and laser vibrometers in there. Okay, so we've done various different testing with collaborating with different organisations, as I said, around Europe and around the world. So the top left is a tidal blade for shuttle hydro. We tested that earlier this year, and their next generation blade has just arrived in our lab that we'll test in early 2021. Top middle is ORPC, which is an American company. We did some testing on their blade and the connection, and then that turbine was sent off to Alaska, and it's currently the longest running turbine in the US. On the top right is a test that we did for Open Hydro a few years ago, and they were very interested in not only the blade but also the connection in there. So the little colour, the image is changing on the right hand side. That's the DIC. We're measuring deformation as a result of the applied load onto the blade. Bottom left hand side is the most recent test campaign that we just completed. That's a 1 megawatt tidal device, which is for orbital marine power. We did a static test and a fatigue test, so we've shown that the blade was good for over 20 years. I'll do a little bit more talking about that in a few minutes. And the bottom one is the 13-meter blade that Will talked about there, which was manufactured by Aero Composites and has a Suzlon involved as well. Okay, so let's get on to the next slide. So this is the latest project, I suppose, within the lab, which is static testing of tidal turbine blade. So this is the largest load that was ever put on a tidal turbine blade, from our understanding. It was just over 1 meganewton of load, which is equivalent to 10 double-decker buses in it. So that blade was co-designed by ourselves with our BladeCom software. The lead designer was Finlay Wallace in Orbital Marine Power, and then that blade was manufactured locally in Galway in Aero Composites, put into our lab, and we tested under static load. As I said, the largest static load ever put onto a blade. We had developed a digital twin using our BladeCom software beforehand, so we could predict how it was going to perform. Then it was performed in the tested in the lab. We scanned it with a 3D laser scanner in there, so the images on the left is from the 3D laser scanner at different levels of load. The image on the right hand side is a plot of the blade deflection against blade length. So the dashed lines are associated with the 3D scan. So the dark dashed line is the 100% static loading. Then you have the triangles. It's from the measurements from the displacement transducers, which match up well. So they're both physical measurements in the lab. And then the circles are associated with the model. So it's not a bad match, but you can see there's a bit of differences. So that's without changing the model from its initial design model. Of course, during the manufacturing, things change, and we'll update the model according to that. So I'll speak about that in a second. So we've just completed the fatigue testing of that tidal turbine blade. This is the fatigue testing in the lab. You can see that in there. So we've shown that the blade has more than the equivalent of 20 years life in it as a result of the fatigue testing that we've completed. As I said, we could see that the model and the was given us a different prediction, slightly different predictions in the actual measurements in the lab. And what we've been doing is during the manufacturing process, we've been following that process. We've been scanning the blade at different stages in there using our 3D laser scanner, and then we can compare the actual as-built blade compared to the initial design. Then we update our digital twin, and then our digital twin then can be used in to predict further how this blade might perform in the future. We've collaborated with lots of different companies, different organizations, so on. This is a sample of some of the companies and organizations we've collaborated. We're always very interested and in speaking to people about collaborations and future projects. And any questions you have, we'll take them in the questions Q&A afterwards, or if you want to type them into the Q&A in there, we'll pick them up along. We could answer them as we're going along, as well as at the very end. So that's me finished. Thank you very much.
Thank you, Jamie. And as I said, for those that have questions, please type them into the Q&A, and we'll have the Q&A session after the presentations. Our next presenter is Dr. Julie Tuin from TU Delft in the Netherlands, and she's going to present on rain erosion and wind turbine blade research at TU Delft. Thank you, Julie.
Thank you, John. So I want to discuss with you a little bit more on what we do in terms of rain erosion and blade research at the Faculty of Aerospace Engineering at TU Delft. And of course, focusing on what we see as the future challenges. So you can go to the next slide. And basically the challenges that we focus on are rain erosion. Let me first see, rain erosion, and then to the next click. And then how do we make the blades of the future, and how do we remanufacture the blades of the future? So basically, how can we design the manufacturing technologies for future blades and generate the knowledge on materials and manufacturing that is needed for the future? I believe that we probably should go for modular blades made out of several pieces, which we then can join together. So that we can wisely choose which materials to use where and which production processes to use where. This will also help us in identifying which manufacturing processes we should develop. Next. Okay. And first I want to discuss a little bit on erosion, and William, if you can click on the video, so on the bottom left, there should be a video. So first of all, I want to talk to you about the erosion testing. So first of all, what we do is we have an erosion tester where we can subject a sample that is coated with rain, and then here you see the process of the samples that we have and how it is subjected to the rain. And what do we want to do in terms of rain erosion? We actually want to understand the mechanism of erosion through experiments, as you can see in the video, where we then can study the damage and through simulations predict the coating lifetime. So in the graph, what you see is the damage growth over time when subjecting a sample to this rain erosion that you see. And we can measure several things. And I will go into this graph a little bit in the next slides. If you can click the next click, so what we want to do is go back one, we want to understand the mechanisms. Then, of course, with the knowledge that we're generating, we want to simulate this behavior, predict the coating lifetime, and then in the end, design the coating materials and production processes for improved erosion behavior. You can go to the next slides. So if we talk about erosion, there are two distinct phases. We have an incubation period where it seems that nothing is happening from a visual point of view. And then we have, once we have damage, then the damage will grow. So that's the damage rate. So first, what is important to understand is the incubation period. So what you see on the left top corner is basically the sample in the grips. And then several locations where we subject the erosion jet towards. We do tests at several speeds between 120 and 200 meters per second. We have a 2 millimeter droplet size and just a normal impingement, so 90-degree impingement angle. Next. And basically what we see is when we look visually at the coating, that's the gray images. When you look at the images in color, that's basically the surface images. On the left top, or at the top, you see that there is no damage yet. And then when you see there's initiation of surface damage, then you clearly can see that in a microscope picture that there is damage. That's when we call it the incubation period. Next. Yeah, so basically with knowing the incubation period at several speeds, we can set up the VN graphs. So that's linking the velocity with the number of impacts, raindrop impacts in this specific case. And from that, we can actually see whether the coating material that we use during the experiments follows the Springer surface impact fatigue graphs that are next on the slide. And what we saw is that our experiments actually align very nicely with the Springer model. So we can use the Springer model to estimate the incubation period for the specific coating that we used. Then once we know the incubation period, then we're interested in the damage itself and how it grows. And here you can see, if you click next. So what we did is we had accelerated testing for erosion, and basically each spot that you see is 30 minutes on top of the other one. So that increases per impact, per location. You see 30 minutes extra of erosion would lead to a certain amount of damage. And then what we investigate is basically the damage, so the surface topography and the damage radius, so that we can deduce the mass loss from that. And we measure that for each spot. And then you get to the graph that we had before. Where you can then, if we look to the next graph that is shown, if you look at the 0 and 1, that's basically the incubation period. So it's just a spot location. It's not yet with time or number of impacts. But what we saw was indeed that we have an incubation period, we have some acceleration, we have a maximum erosion rate, and we have some deceleration before the speeding up and getting to the terminal stage, basically. And you can measure now the damage radius, that's the one that you see being portrayed on the screen right now. But we can also get the volume loss because we can get the surface topography. And then you get some information on, with time and number of droplets hitting the surface, you get the information on the erosion behavior. So that's on the next graph as well. There you can, of course, if you have the volume loss, you can calculate the mass loss. Next slide. And what do we use this for? Now we have this lab testing, right? But actually what we're interested in is being able to analyze the erosion of wind turbines out there, in our case in the Netherlands. So we want, of course, to set up a model that can predict for a specific site the erosion of a certain turbine. So here you see an analysis that is being done for several sites in the Netherlands. We have very nice meteorological data for a long time, so for more than 25 years for all these locations. And we can use that to see the effect of the site itself. So we do a probabilistic model. So if you click the next one, we can estimate the damage based on the probability of occurrence of rain and wind conditions at a given site. That's based on the meteorological data. And then the short-term damage defined by the Springer's surface fatigue model, as I've just discussed. And based on that, we can then predict what is happening in the Netherlands with erosion. And then we can basically see that the ones close to the shore have a lower erosion lifetime than the ones in the center of the Netherlands. And what we also saw is that orography plays a big role. Then moving on to some manufacturing processes and remanufacturing processes. Well, basically for all processes, it is important that we understand materials and processes because then we can predict and of course eliminate process-induced defects, which we research through material characterization, process modeling, using of smart molds and experimental validation. And for liquid composite molding, we, for instance, look at residual stresses, void formations, and wrinkles. And then for the next one, we also look at in situ consolidation due to laser-assisted fiber placement. And what you see on top is basically a layer of thermoplastic composite, which is laid upon a substrate. And when you zoom in, what you see is that there's voids between the tape and the substrate, which you actually do not want for quality purposes. Next one. What we do in terms of multi-objective optimize, or for liquid composite molding, we use multi-objective optimization so that we can optimize both for cure time and product quality at the same time. So basically each dot that you see on the graphs has a optimal cure cycle linked to it. So you can then choose as a producer, blade manufacturer, I want to get minimum cure time of something, then you know what your product quality is. Or you say the product quality is way more important, and then I have to sacrifice my cure time. And then you can select basically on the material properties that you use, what the optimal cure cycle is. And we, of course, also want to validate it. So we have some molds representative for blade manufacturing with sensors involved so that we can actually create digital twins for the manufacturing process itself. Next one. Multi-objective optimization, what we did is we simulated a whole root insert and looked at the spring-in due to a certain cure cycle, and then used the multi-objective optimization to look at whether we need a fully coupled thermomechanical model to actually investigate that. You can click. Yeah, and there we saw that, again, you see the two graphs, process time with either overshoot temperature or spring-in. Spring-in is a fully coupled thermomechanical model, and overshoot temperatures is just a thermal model. Normally, the thermal model is used as a measure, and the overshoot temperature is used as a measure for the product quality. And what we saw is, if you go to the next one, oh, sorry, one back. Yeah, we saw a significant reduction in cycle time while also increasing product quality compared to what is recommended by the manufacturer of the resin, for instance. So typically, blade manufacturers just use whatever they have, whatever they know. And here we could get a serious reduction in cycle time. When spring is important, then you definitely need a thermomechanical model fully coupled. We also gained quite some insight in stress buildup in the laminate. And it actually will enable also green process design, digital twins, process monitoring. When you use new materials, you just put it into the model and basically your optimal cure cycles come out. Next one. In terms of in situ consolidation, so due to laser heating, we heat up the thermoplastic and now we roll over it for the next layer. Next one. We have a setup with a laser inside the lab, as you can see, with a thermal camera to observe things that are happening. Next one. And basically what we saw is when you have this rapid heating, then you get deconsolidation of your tapes, which is very interesting, but because that will drive the intimate contact models are not valid with these laser processes. So what we're doing next one is developing the intimate contact models. Next one. What we also look at is weldable interfaces for thermosets. So normally you can only weld thermoplastics with thermoplastics, but if you do a smart trick and you mix thermosets with thermoplastics, they create an interface. Then that's basically what you're seeing on the screen right now is the interface. On the right side, you have epoxy, on the left side, you have PEI, and it creates an interface. We're trying to understand that interface formation and the strength of that interface to, next one, to be able to weld epoxies with thermoplastics. So there you see some samples that we have welded. Next one, next one. And I want to thank, of course, I cannot do this on my own, but I want to thank my research team. And then if there are any questions, next slide, let me know and feel free to contact me.
Thank you very much, Julie, for a very interesting presentation. We are presenters, two presenters from this session aren't available yet to present, so we'll move into the next session before the break, and Dr. Mark Hardiman from the University of Limerick will present on testing and classification of high performance blade protection materials. So there's good complementarity with the last presentation. So Mark, if you're ready, thank you.
Okay, thank you, John. So William, if you have my presentation there.
I don't have it, Mark.
Oh, I emailed it to you. Okay, I can share my screen if that's okay.
Yeah, sorry. I must have missed it.
No worries. It's 1 second. Okay, so can you see that there?
Yeah, that's all perfect, Mark. Thanks very much.
Great. So hello, everyone. So this is just a brief presentation on some of the work we're doing down here in Limerick on testing and classification of leading edge protection materials for wind turbine blades. So as mentioned, there's a lot of synergy with what Dr. Tuin just presented. So we've seen this in the last two talks where rain erosion is a big problem for the wind turbine blade industry. As was mentioned, it's kind of like death by 1,000 cuts, where you have very high velocity rain droplets striking the leading edges of these blades, and damage can begin as early as 2 years, requiring maintenance. Obviously, with the more maintenance you have, the more downtime you have. Downtime equals energy not being generated. So it has a significant financial repercussions due to this phenomenon. So the damage typically starts as light pitting as the first stage of damage, and the damage propagates from there. So next slide, please. Oh, sorry, to me. So in the University of Limerick, Dr. Edmund Tobin created and manufactured the Wearer, which is the whirling arm rain erosion rig. So as you can see here, if you can see my mouse, we have a rotating arm, which our sample is adhered to the end of the arm, and that travels at a high rotational velocity around the inside of the chamber. So along the outside of the chamber, we have our water dispensing needles, which emit droplets of around 2 millimeters. And obviously, as we move around, we strike, or our sample will strike the droplet, resulting in erosion of the sample. So, as mentioned previously, typically we measure this rain erosion in terms of the mass loss of the sample. So we'll take the sample out of the wearer at various time increments and weigh the sample. So typically we have an incubation period where we see very little or no mass loss. And then at a certain point, incubation finishes and we get steady mass loss. So typically we rate the materials by the incubation time and the total time to ultimate failure. So the wearer operates between 128 and 178 meters per second, and this is designed to simulate rainfall of 25.4 millimeters per hour. So typically what we expect is kind of like this curve A here, where we have no mass loss during the incubation period, and then we get a steady state linear mass loss after the incubation period has finished. So typical results, this is kind of your standard example of a polymer on a glass fiber reinforced polymer substrate. Here you can see after 10 minutes, we were still in the incubation period. After 15, we started to see some mass loss. And for the remaining time increments, we saw an increase in the damage on the surface. And after 45 minutes, we had damaged the coating all the way down to the filler between the GFRP substrate and the coating. So I guess our recent test campaigns have not just been looking at ranking different materials in terms of their erosion, but also trying to get a better insight into why some materials perform better than others. So in a recent experimental campaign, we analyzed the rain erosion response of a number of different polymers, PMMA, PC, PE, PET, and polypropylene, PP. And if you look at the mechanisms of erosion, we should be able to link the rain erosion response of these materials directly to the material properties. And this ideally would forego the need for rain erosion testing. We could just choose materials based on their properties, which are much more easily ascertained from standardized mechanical testing. So we were able to rank the materials in terms of the incubation time and the total duration within the wearer. And we were also able to measure the mass loss rate. So once incubation was finished, how quickly it was losing mass and the damage was propagating on the coatings. So what we did then is we tried to look at other techniques we could use to characterize these materials. And one very useful technique was the use of nanoindentation, which is essentially a very small scale hardness test. So this allows us to characterize not only bulk materials, but also coatings that have been applied to our composite substrates. So we can actually characterize the coatings in situ rather than having some kind of representative material value. So we looked at a lot of different parameters that we could take from the nanoindentation test. We look at the correlation of storage modulus, kind of the elastic component of these viscoelastic materials. And we saw a correlation that as the storage modulus reduces, we get an increase in duration. So unlike metals, the storage modulus or the elasticity of the materials was better off being low than high. And similarly for the indentation hardness, we also saw a correlation between a reduction in hardness and an increased time to failure within the wearer. Nanoindentation also allowed us to analyze the effect of recovery. So as we load up to the maximum load, we can look at the instantaneous elastic recovery, but also monitor the viscoelastic, the time-dependent recovery of the surface after the load has been removed. Okay, and we saw that, as you kind of would expect, that the materials that bounce back faster were more resistant to rain erosion. So they typically can bounce back before the next incoming rain droplet. And we looked at both short-term and long-term viscoelasticity or viscoelastic recovery of these materials. We also correlated the rain erosion response with the surface properties. As you can see here on the coupon, we looked at the surface profiles at various different regions towards the kind of failed wear scar area. And we saw, as you would expect, as you move towards the wear scar, the roughness of the surface increases. And what we found was that each material had kind of a property, almost like a material property, where there was a what we called a critical roughness, below which there was no massive mass loss. So as long as the roughness was below these values, there was no, or it would still be in the incubation period. So this was quite interesting, and it's something we're using for other projects as well. Another critical aspect is the interface between the coating and the substrate. So far we've been kind of looking at where that initiates from the impact, or rather here, the impact between the water droplet and the coating. But as this stress propagates dynamically through the coating, you have an interaction with the substrate. So what sometimes can happen is, as we've seen, you get wear at the top surface, but you can also get these interface failures or delaminations between the coatings and the substrates. And we have an example of one here where on a recent project with the European collaborator, we were able to observe delaminations because we were looking at transparent polyurethane leading edge protection systems. So you can see here on the top surface, when we focused the microscope, we had little to no damage or mass loss. But if we focused on the interface between the coating and the substrate, we saw the initiation of a delamination, which then propagated with more time within the wearer. We're also looking at multi-layer coatings, so analyzing the effect of adding primers and the effect of having the filler. And again, we can use nano-indentation of the cross-section between these various layers to analyze or directly measure the in situ stiffnesses of these layers. So we can see that we were able to identify the stiffness parameters, which correlates with the acoustic properties of each material. In terms of the research direction we're going in with our latest SEAI project, obviously we're keen to collaborate as part of the IEA TCP on a task on rain erosion. And really we're looking at carrying out more time-dependent characterization. So obviously rain erosion is a repetitive dynamic event rather than a quasi-static one. So here we're trying to focus on more high rate and viscoelastic characterization of these materials going forward. So this can be impacts testing, or we have a rig here in Limerick for high rate tension and compression characterization of viscoelastic materials. So we're developing methods currently to not just characterize the materials quasi-statically and try to relate the ranking of the rain erosion resistance with those properties, but also trying to develop novel methods to look at higher rate. So this also includes ultrasonic characterization, so characterization of the speed of sound through the material and the various layers of the material. We're looking at various experiments using more nano-indentation, but also scratch testing to analyze the interface characteristics between the leading edge protections and the coatings. So essentially trying to characterize the normal and shear strengths and energies, which can then be input as or used as an input into kind of cohesive zone modeling using finite elements. And obviously we're dealing with various environmental conditions as part of this global problem. And obviously with various environmental aging, these properties will all change. So we need to kind of apply these characterization techniques to various types of aging of these materials also. So that's just a quick overview of the work that's being done currently in Limerick. If there's any questions, feel free to fire them into the Q&A chat that we have on the Microsoft Teams here, or if not, feel free to contact me directly by email. So thanks very much for your time.
Thank you very much, Mark. Again, it's good complementarity of the last two presentations. Our next presentation will be on, we've run into our second session. We'll try to bring the missing presentations from the first session after the break. So our next presenter is Dr. Paul Leahy from University College Cork, and he's presenting on the EU Rewind project, which is looking at end-of-life considerations for wind turbine blades and particularly sustainable repurposed products from decommissioned composite material. So thank you, Paul. If you can go ahead.
Thank you very much, John, and thank you everyone for attending today. I really welcome this opportunity to introduce our project Rewind. We are looking at the end of life of wind turbine blades. So we're looking at what happens once the blades have been taken down due to either wear or decommissioning of the turbines, and what to do with the composite material wind turbine blades. I think, as most of you know, recycling or recovery of composite materials is difficult and problematic and expensive. So we're proposing a different paradigm in this project where we're looking at repurposing. So the work that I present here is work of a multi-institution project. It's been funded by SFI in the Republic of Ireland, by Department for the Economy and Invest Northern Ireland and by the National Science Foundation in the USA. So it's a tripartite project. We have partners Georgia Tech, Queen's University Belfast, UCC, City University of New York, and we've recently been joined by CIT as well, who are working on one of our repurposing projects. So the challenge really is a circular economy challenge. We all know that wind power is a sustainable energy resource. And we know as well, of course, that wind turbines produce many more times energy during their lifetimes than the embodied energy in their manufacture. And the life cycle analysis shows that they recover their debt in terms of their embodied materials several times over. So that isn't a problem. However, the blades are primarily composed of non-biodegradable glass fiber reinforced polymers for the most part. More recent models may include carbon fiber reinforced polymers, but this is a legacy problem really at the moment. So we're looking at wind turbines that are going to be decommissioned in the next decade to 2 decades. So what we're doing really is looking at what was installed in the early part of the 21st century. And when we look at the incoming volumes of waste from decommissioned blades, that's expected to reach 40 million tons by the year 2050 globally. And the current solutions are really not environmentally sustainable for future generations of blades. So current practice includes incineration. It includes simply stockpiling in some places. It includes landfill. Many blades are ground up for aggregates, and this is, probably one of the more sustainable solutions at the moment. But we believe that, this is not a long-term sustainable option for the end of life of wind turbine blades. So the question really that we're posing is, can a feasible repurposing option be found for this composite material in blades? Looking more locally in Ireland, the success of the wind energy industry in Ireland has driven the amount of turbines that have been installed here. When we look at this graphic here on the right-hand side, we see the growth in terms of the number of turbines to be decommissioned. So this is the cumulative number to be decommissioned over the next 2 decades, reaching over 2,300 turbines to be decommissioned by 2038. So what to do with all this decommissioned wind turbine blade waste? Again, solutions such as landfilling lie at the bottom of the United States Environmental Protection Agency's waste hierarchy. These are the least preferred. Better to move up the chain and move up through at least recovering some energy, recovering some materials, or ideally reuse. So that could be entire reuse on a second-hand market and reinstallation, or it could be repurposing. And this is where the Rewind project sits. It sits in terms of repurposing, taking the manufactured products of wind turbine blades and turning them to new uses. So this is our methodology. The first thing we did early on in the project was that we brainstormed 50 different concepts in a workshop in Belfast, and then we basically focused in and developed some of these in more detail. It's not just a technical feasibility problem, it also is location specific, due to the fact that wind turbines tend to be located in relatively remote areas in many instances. Maybe there's poor access, and they're also deployed into a particular social, environmental and economic context. So whatever we do with the blades at the end of their first life, bring them into a second life, we need to be sensitive to these factors when we come up with repurposing solutions. So to this end, we took a transdisciplinary approach. The Rewind team includes architects, structural engineers, sociologists, energy engineers, business model specialists, and geographers working on GIS. And we've taken a whole range of different techniques in order to attack this problem. So we have carried out 3D LiDAR scanning of blades in order to infer their geometry and then try to infer the structural properties, structural analysis and testing methods in Georgia Tech. We're also doing life cycle analysis, so we're looking at the environmental performance of GFRP and repurposed products made from GFRP here in UCC. And our goal really is to come up with a robust set of internationally deployable success indicators for repurposing projects, incorporating environmental, social, and economic concerns. So just as a sample of some of the work done in Rewind, this work was done in Queen's University, Belfast. We have a geodatabase of wind turbines installed in Ireland, along with their projected decommission dates. So this database can be queried by location, by turbine type, by the dimensions of the blades, and by the projected decommissioning date. So we can ask questions like, where can we find blades that are between 40 and 50 meters long within 100 kilometers of Galway City? And this is useful when it comes to looking at repurposing options because many of them are highly localized. So here's an example. This is a design that's been developed in Georgia Tech by a very talented undergraduate student, Zoe Zhang. in collaboration with the Wind team at Georgia Tech. And this is a 5.5 meter footbridge for installation on a proposed greenway, while on an under construction greenway project. And this will be designed using blades from a Nordex N27 turbine. We will use a third similar blade for doing some structural testing. Part of the work here, part of the, some of the most kind of innovative work is looking at different types of fasteners and how to fix the wooden elements of the bridge to the GFRP of the actual wind turbine blades. And some innovative thinking was needed here in order to develop solutions that are easily assemblable on site, because sometimes these bridges may not be transported in a single piece to a site, and that they can be, the designs can be replicable even if the blades themselves change, because there's a wide variety of blades feeding into these designs. Some other concepts that we were looking at as well, so roofs and cut from blade sections for emergency housing, and power distribution poles developed from wind turbine blades, which is in development at Georgia Tech. Looking at the environmental performance of the bridge design in particular, this is work that's been presented just this week by, or last week by Angie Nagel, our PhD student at the Recomp conference on composites, reuse and recycling. So we're looking at the construction of this pedestrian bridge in County Cork. We're sourcing blades in Northern Ireland. The lower 2/3 section of the blade will replace the steel girders that would otherwise have been used in the bridge. Steel is actually a reasonably environmentally friendly material because most steel used in construction is actually recycled. The top 1/3 of the blades, so the tip sections, which don't have the structural strength for bridge applications, they're taken off, and we're assuming that they're going to be sent to landfill, although we hope that we'll find a more suitable solution for them. There will be an additional coating just for environmental and aesthetic considerations. And then the end of life, we need to think of the end of life of the actual bridge as well, even though bridges are long-lived structures. So this will be co-processed in a cement kiln disposal route, which is, of the current disposal methods, probably one of the preferable ones, as previous work has shown. And then we have to consider all the other materials such as fastenings and decking material, the concrete abutments that the bridge will sit on, in order to feed into the life cycle analysis and come up with the overall environmental impact study for the bridge. When we look at this and we look at our baseline scenario, and our baseline scenario is co-processing. So what we mean by co-processing is we mean grinding down the blade material, putting it into cement kilns and co-firing it in cement kilns with conventional feedstocks in cement production. So that is basically a form of energy and material recovery. It's not currently carried out in Ireland, it's done in Germany. So there's a transport cost associated with this if you do it under the current situation. So negative numbers here indicate superior environmental performance. So basically, co-processing is environmentally beneficial because we're displacing some of the alternative fuel and feedstocks in cement construction. But if you look at the dark green bars, which are the bridge construction, you can see that it outperforms. So it's a greater negative impact than in every category than the best of the current end-of-life solutions, which is co-processing. So we think we found evidence-based solution here for sustainable repurposing application for wind turbine blades. So we've shown that it's technically feasible, and what we're seeing already is that our chosen baseline for this study, which is cement kiln co-processing, that is in turn superior to landfill. So even co-processing is superior environmentally to landfill, and the blade bridge is better again. So we're finding that repurposing does indeed perform better than alternative end-of-life options for wind turbine blades. And the next step is combining the social and economic assessments with this type of LCA life cycle assessment environmental work, coming up with a holistic overview of the best overall solution for dealing with end-of-life wind turbine blades. And Peter Deeney, our postdoc, has a paper currently in review on this topic. So I hope I've just given you an overview and a flavour of the ReWind project and some of our work. It's a very broad and multidisciplinary project, so there's lots of activity happening at the moment. happy to answer questions in the Q&A session later on. Thank you.
Thank you very much, Paul, for a somewhat different but complementary project in terms of looking at the full breadth of the life cycle of the wind turbine blade. As I said, we'll take our answers at the end of the second session, or questions and answers at the end of the second session. We're going to take a short break now to regroup. Hopefully we'll be able to bring the missing presentations from the first session online and complete the rest of the presentations also in the second sessions. I believe our break is 5 minutes.
Yeah, 5 minutes is fine.
5-minute break, so we'll reconvene at around 7 minutes past. Thank you.
Thanks, John.
Hello, welcome back. We're moving now to the next presenter on the agenda, Professor John Costello of Dublin City University, who is going to present on something completely different, which is laser ablation for wind turbine blade contaminant removal. So over to you, John.
Okay, thanks, John. So this is a project which is just starting. By way of background, we're a high power laser applications group at DCU, and we do a lot of laser spectroscopy. So we're really going to talk about laser ablation for surface cleaning, and then a thing called laser induced breakdown spectroscopy for contaminant analysis. So the main motivation actually for this project came from the SB and SEAI initially, because when they published the call for proposals, one of the proposals that came, one of the ideas that came from the SB was this idea of being able to remotely diagnose contaminants on wind turbine blades. And so obviously our own group, we looked at that and we thought about it, and we said, well, actually LIBS, or what's called standoff LIBS, or laser induced breakdown spectroscopy, would be a good solution. So in fact, as everybody probably on the call knows, the aerodynamic performance of the wind turbine blades depends critically on surface structures. And so actually, when you looked back in the literature back to 2001, there was an experiment carried out with two wind turbine blades where effectively one was kept clean and one was not. And over a 2-week period, one could see, I think it's on the next slide, one could see up to about a 40% reduction in the sort of conversion efficiency, so in the power output from the wind turbine, which was contaminated by insects. And so it can be a significant problem. We're not saying it'll always be 40%, but it can be a significant problem, particularly when the wind gets up. So we thought we would, and our it's very much a kind of a fundamental research project. This one, it's funded over 4 years jointly by the SEAI and the ESB. It's just started. Like most people, we were locked down. Our labs were shut down until sort of the middle of August. So we've really only been coming back. We needed to put a new team of students in place. So this is very much about what we're going to do. But basically, the idea is that we would look for an alternative to the kind of wet cleaning, which is typically done with wind turbine blades now. And so our proposal was that we would use laser ablation for essentially the removal of contaminations from the surface. And as it turns out, with laser ablation, it's been applied in many applications which are critical and delicate, such as cultural artifacts, paintings, and so on. And so there's a group in Greece at Forth at the Hellenic Research Centre for Fundamental Research who've been doing this for a while. So on the next slide, we really can come to the main solution. Can we, William? Is it you on the slides? Ah, great. So essentially, our overarching objective is to develop and apply standoff laser ablation and laser-induced breakdown spectroscopy for both the removal of contaminants and simultaneously the analysis of the contaminants as they're being removed. Because when you fire the laser onto the surface, you generate a plume of material, much like the picture you see in the middle there. And that plume of material is emitting. So we can capture the light, analyze it, and from doing spectral analysis on the light, we can classify what contaminants are present. And under certain circumstances, we can even quantify the contaminants present. Most of our experiments, which we do currently, we do in the lab, typically in a chamber like you see on the right-hand side. And we use one or more laser systems, as you see on the left-hand side, for doing the laser ablation, and then various cameras and so on for doing the analysis. So the next slide, please. So that's a video. I don't know if you can get it running. Yeah, there you go. So essentially, you usually would hear that, but essentially what you can see, we're just moving a piece of contaminated metal in the laser focus. And essentially you can blow away the material. And the key, the main things we have to try and develop from this project are what are the laser parameters, the focusing parameters and so on, which allow us to be able to remove contaminants, but at the same time not damage the surface. So that's really what we have to do. And to do that, we need time-resolved spectroscopy, time-resolved imaging, both spectral imaging and so on. So on the next slide, I don't know if we can, can you see the play bar? On the next slide, what we're doing is, maybe it's not working, is it? Is there a play bar there?
It doesn't seem to play.
Beggars. Right. Anyway, doesn't matter. So basically, with our cameras, one of them we use as a fast framing camera. In fact, we've a few of them, but typically that would have an exposure time of maybe a few nanoseconds per frame, and we might introduce a time delay of 10 nanoseconds per frame. So that basically allows us to be able to see the evolution of the ablation plume in space and in time, and also spectrally analyze it. So you can see in the schematic diagram there, that's a typical setup we'd have, where we'd have two of those cameras, one of them doing the imaging and one of them doing spectroscopy. So essentially, in terms of laser-induced breakdown spectroscopy, it's essentially an analytical technique allowing us to identify and quantify low concentrations of trace elements. And it's very simple. It's you can take your laser pulse anywhere. You just focus your laser pulse onto the sample, make the plume, capture the light, and analyze it. If you go to the next slide, William. So that's typically, you might see a spectrum that looks like that. This happens to be iron with some carbon, sulfur, and so on in it. Usually, what you have, if you're after particular elements, you will have reference targets with known concentrations. So we'll generate a calibration curve, like on the right-hand side there. And then the real question, if you're an analytical scientist, is, well, how low can you go? And we can get down to limits of detection in parts per million. In remote and standoff, where you have lots of fluctuations and statistical fluctuations, typically you might be looking at something like 100 parts per million. So on the quantification side. So we use the wavelengths to identify, we use the intensities to quantify, simple as that. So if you go to the next slide, very often people are not really interested in what the specific contaminants are, but they want to be able to classify them into groups. So very often, if you see that there are lots of contaminants which have spectral signatures which look very much the same, then we will just look at principal components. My colleague Paddy Hayden in UCD does that, or support vector machines, or convolutional neural nets, or some statistical analysis technique to be able to separate them out. So we envisage applying chemometrics, because you're really talking about organic contaminants, and it's carbon, it's nitrogen, it's oxygen. And so the difference between different contaminants or pollutants mightn't be that great. If you just go back one, sorry, just to the next slide, where you see, essentially we've broken the project into a number of work packages. The first three are the main ones. We've recruited 3 PhD students recently onto those. The first one is basically going to develop a system which we will deploy in the field. The second one is largely working on the parameters that we need for LIBS. And the student Ross Murray in UCD will be working on the actual laser ablation cleaning. We need to know the material properties. We need to understand the laser interaction with the surface, so that we don't damage the surface. We can remove the contaminants. In fact, the spectrum will change slightly, of course, when we remove the contaminants. And that will be a sort of an end of plasma process, an end of process to tell us to stop firing on that spot, and so on. And then there's some extra pieces we want to do around other things other than remote standoff. So if you go to the next slide, you can probably see some pictures of what typical standoff systems might look like. So the bottom left-hand side there is the system which uses a Cassegrain telescope and a couple of lasers for what's called dual pulse LIBS. That's the kind of system we're proposing to use in the first place. And if you look at the top left-hand side there, the very first paper we've ever seen using standoff LIBS for an electrical application has just been published, actually, in Spectrochemica Acta. And there they're looking at the insulators and looking essentially for signatures which show aging in insulators as pylons age. So the idea there is we use the telescope, essentially an astronomical telescope, to expand up the beam so that it's large diameter, and then focus it gently towards the wind turbine blade, which could be, say, 100 meters away. And then the same collecting mirror on the telescope, the same objective mirror, collects the light, focuses it then via fiber optic down into our spectrometer and do the analysis, or else focus it directly onto a camera where we can do some spectrally resolved imaging. So that's our so we're doing laser ablation and LIBS all with the one system. So we're doing the cleaning and analysis all with the one system. And as I say, you know, you can see the signatures of the contaminants. When you hit the surface, you'll see the signature of the surface, and then essentially you stop and you move the laser. So there's an issue about scalability. So we go to the next slide. I mean, one of the challenges we'll have is essentially, how do we do this? So do we do it in the traditional way with the cast-grain telescopes and so on, which we intend to do? But we should mention, it was actually in conversations with William and Jamie Goggins actually, that they talked about the other possibilities, which were projects around drones, which are something we thought about in the proposal, but also there's kind of Klingon robots, that systems that are around, and we can certainly think about adding modern type laser systems to those which produce pulses with millijoule energies in sort of 100 nanoseconds, which is sufficient to do the ablation, the LIBS, the cleaning, and so on. So that's an alternative, just to mention it there. So on the next slide, if you want to start looking at how do you scale it, I suppose the big number there is if you took 1,000 square meters of surface, you would be looking in the range of, you know, few hundred to 1,000 minutes per 1,000 square meters. So just to give you an idea of scale up, for that you need a laser with a pulse repetition frequency about 100 kilohertz. But obviously you can reduce that by a factor of 10 if you go to these megahertz lasers. So a lot will depend on the pulse energy that we figure out we need, the wavelength we need, or do we work with the fundamental of the laser, do we need to generate harmonics, which are less efficient, and so on. In terms of LIBS, the timescales will be shorter, because one can imagine you don't need to cover the whole surface. You might choose grids which are sort of on a scale of 10 centimeters. So you might have a spatial frequency or a spatial period of 10 centimeters. And therefore you can dramatically reduce both the requirement on the laser and the time taken. So typically you could do a whole analysis over 1,000 square meters in something like less than an hour. So that's our proposal. I think in the next slide we might have pictures. We're starting to set up the labs. So, oh no, just to mention to you that the actual laser technology to do what I said, which is the high rep rate stuff, we don't have it. But that laser technology is now becoming commercially available. It's fiber-based laser systems, which typically have average powers in the couple of hundred watts to a kilowatt. They're producing sort of millijoule pulses at megahertz repetition rates. That's basically where you're getting your 1,000 watts. These are the labs we're setting up for the various work packages. So these are where the guys are working at the moment. We essentially have broken it into the 3 work packages. Work package 4 shows you our ultra fast laser labs. So 4 of those labs are in DCU. The middle bottom lab is the lab in UCD for the ablation on the surfaces. So we are putting we're essentially repurposing a lot of these labs for this particular project. And we're getting there. We're having to train up the students and everything. But we certainly expect to be, we have samples already from Jamie and William. So we certainly expect to be running just before Christmas with the first samples, and really be into this project afterwards. So we're near ready for measurements. We have to establish the real world laser and focusing conditions. The test stand that we build as part of this project, we expect to be actually useful in the field because it's about the right rep rate. We will certainly establish the parameters, but if you want to build a real commercial solution, then you're really talking about the new laser technology and a couple of orders of magnitude up in the kind of funding levels to do that. So that's where we're at. Just on the next slide, just to acknowledge the people who are advising us and helping us from the SB, from samples and so on, and discussions with Jamie, the SEAI. And in terms of the standoff, we have long-term collaborations going over decades. As you can see from me, I've been around a while with various people. But in terms of standoff, LIBS, laser ablation, Rick Russo's lab at Lawrence Berkeley Lab in Berkeley and Javier's lab in Malaga are probably the 2 best, and we have collaborations with those. So we're just starting, we're getting ready to go. And I'd hope in a year's time, if we have one of these projects, we'd be able to report some real results to you. So thank you very much to everybody. That's it from me.
Thank you very much, John. Again, some lateral thinking there on a new solution to an old problem, and certainly may reduce a lot of maintenance headaches for wind farm operators. Our next presenter is Dr. Edmund Tobin from the Institute of Technology in Carlow, and he'll present on a droplet impact erosion mill, which is again an SEAI funded project between the Technical University of Dublin and the Institute of Technology, Carlow. So over to you, Edmund.
Thanks, John. Good afternoon, everyone. So I'm going to present on our project here, the Droplet Impact Erosion Mill DM. It's a collaboration between TU Dublin Crest and Engcore IT Carlow. So the main members of the team are Professor Brendan Duffy at TU Dublin and Dr. Joseph Mohan, and then myself leading the IT Carlow part with Mr. Alistair Chambers. So the general project, it's a one-year funded project to the SEAI Natural Energy Research Development Demonstration Fund from 2019. Started officially in January 2020 with a 12-month duration, which will be extended with agreement hopefully in the next short period. So the main idea of the project, and as you've seen already by what other people have presented, rain erosion is very common on wind turbine blades. This is a known problem for many, many years. The problem was previously seen on aircraft. So the model of the impact is well known. It's not very easy to ascertain whether a material is good or bad when it comes to its rain erosion resistance. And so many attempts have been made to develop test rigs to prove materials resistance to that droplet impact. So the TU in Denmark have developed a water jet test rig, which we are using as our baseline design. So we're hoping to develop a slight variation on that with our own ideas. And the main kind of standard rig is a whirling arm rig. So the wearer test rig in UL, Dr. Mark Hardeman has previously spoken about this. I worked on developing that test rig during my PhD and doing some time doing research at UL. So the whirling arm rigs are described as the gold standard because we don't have any other method of doing it. Depending on whether it's a wind turbine manufacturer or an academic institution, the idea is still based on the idea of accelerating a sample to a velocity which is equivalent to what will happen in reality and adding water droplets to that whole system. The main variations between the systems is whether it's going to be a multiple arm system or a single arm system. Previous projects that we worked on as part of collaborations, TU Dublin and UL would have worked previously as part of the environmentally friendly engines with Bombardier, and solid gel coatings were developed to be attached to the leading edge of business jet nacelles. The main driver of those coatings would have been high gloss finishes, but the main action that was occurring to them was very, very high temperatures with the anti-icing system that was being applied on the nacelles. So there's some examples there of testing and SEM images of the coatings after testing. And that project was followed by Aeromoco, which was led by EADS. And that project was on anti-ice, anti-contamination with a major element of erosion. So the coatings that were shown to be good at anti-icing or good at anti-contamination in terms of removing insect contaminants generally weren't shown to be very good at surviving rain droplet impact. So moving on from that, the current DM project is to develop a water jet test facility with associated testing of wind turbine blades. The equipment is going to satisfy the standard developed, the ISO TS 19392-3, and to develop a training course for wind turbine farm operators on coating evaluation asset management. Specifically, we're using substrates of GFRP and stainless steel to look at the different adhesion conditions and the effect that has on the coatings. Paints to be trialed by AzoNobel and Juntun. We have other coatings that we will have supplied by International Paint. Our trial samples are going to be 100 by 30 millimeters. Thickness is generally 4 millimeters, but can vary. Our test campaign then for each sample will of course depend on the ability of that sample to survive the erosion conditions, and could go from minutes to hours depending on the speed. And we will then assess the damage of the samples based on the ISO and DNVGL standards that are being published and developed in the recent period. So having developed the wearer, I understand what goes into producing a whirling arm rig. And what we're trying to do with the DM is to develop a complementary rig rather than to say that one is better than the other. We know that the wearer, the whirling arm design, is the closest thing to replicating what happens in reality by accelerating the sample onto the droplet. But the water jet system, if it can be proven to be effective at least ranking the materials in the correct order, it can be used as a method of pre-screening of materials before they go for their finalized testing. A lot of money and time is wasted with materials that look good on paper, have been developed in a lab, and are put onto a sample and come off within minutes. So a valid test that can allow pre-screening is really what the water jet needs to give us. So in comparison, we can see that in a DM type system, we can test many more samples within the same test condition. The variability of the test conditions can be removed then from that. The impact angles in a general setup, if it's not a shaped holder, you can only test one impact angle and you have to change your whole system. We hope to be able to make the angle infinitely variable with the DM. The testing time again is just dependent on the resistance of the materials, and we're hoping to develop the rig to test up to 170 meters per second, lower scale 70 meters per second, and in line with the ISO standard, which the wearer of course matches as well. So this is our current mock-up of the design. We have a rotating mill rotating about the vertical axis. And in this way, we hope to allow us to do more tests on a single sample. So we have our jet nozzle producing our high velocity water jet, 0.8 millimeter diameter, and then we have our disc that will chop that jet up into finite slugs so that we'll have individual impacts on the sample. As the jets are hitting the sample, the mill will be rotating. And the main reason for this, it'll allow us to have multiple impacts on the same sample, but not exactly on the same point. And as Dr. Mark Hardiman mentioned earlier, one of the things that has been researched recently and has been mentioned many years ago in aerospace research is the ability for the material to relax after an impact. Some water jet rigs impact at very, very high frequencies, not replicating what happens in reality, and can overstress the material in terms of the impact rate. So with the mill rotating as the impacts are occurring, this will mean that the sample is not constantly being impacted in the exact same position, and will give the material a chance to relax and hopefully start to replicate more closely what happens in the whirling arm rigs. The main concept then is that we will move the axis of the mill, which will allow us to change the angle of impact on each sample, and this will give us in essence an infinite number of angles that we can choose, but we will probably work along the lines of 90, 80, 70, 60, 40. Below that we don't imagine there's going to be much happening in terms of erosion, and that's the main idea behind the mill. The number of samples then, we could go up to 30. We're still deciding on that piece of information. The materials itself, the substrates that we've produced, so they're glass fiber polyester laminates, 15 plies, with plus or minus 45 biaxial layup. And we're looking to also produce some epoxy laminates, and as we mentioned previously, we'll be using steel substrate as well. Samples are 100 by 30 by 4 mil. In the image on the right, we can see the concept that we have for our impact frequency on a sample. Because the samples are quite large, we intend to impact on a lower side of the sample, then invert our mill, so remove our series of samples, invert the mill, and then impact again on the lower side. So this will give us 2 finite impacts on a single sample, allowing us to get more information from that single sample. And this is all based on the caveat that we are not seeing any significant damage translating across the sample, which we don't envisage happening. Yeah, so, and then as mentioned, so currently where we are is we have coatings being applied by AkzoNobel and Junton. They're coating both composite and steel panels at the moment. And this is mainly to look at the failure mechanisms and the differences between failure mechanisms and the adhesion between the coatings and the substrates. Other work that has been completed today, the training course has been developed by TU Dublin Crest, and the discussions are ongoing with ESB on running this course. Access has been secured to some wind farms run by Bord na Móna, which will allow us to visit them during their scheduled preventative maintenance to look at what the in-service turbines, the type of damage that we see on the leading edges of those. And that's basically it from me. Thank you to everyone. If you have any questions, you can ask in the Q&A, or you can get me on the email there. Thank you very much.
Thank you very much, Edmund. And we'll now move back to some of the presentations that we missed in the earlier session. Dr. William Finnegan will deliver Tomas Flanagan's presentation from Air Composites.
Yeah, can you hear me there, John?
Yes, thank you.
Okay, so we've had a few technical issues. So Tomas isn't able to get online, so we used to work in Air Composites, so hopefully I can do this justice without really having seen too much of these slides. So I suppose just a little bit of background on the company Air Composites. It's located in Invern in the Connemara Gaeltacht, and it employs about 60 people. It was founded in 1997. And it's been operating mainly in the aerospace and renewable energies sphere, where it builds large-scale composites or large-scale composite structures. However, it has varied history, especially in R&D, where it also focuses in space applications along with aerospace, automotive, and renewable energy. On site as well, there's a CTL, which is a composite testing lab that's NADCAP approved, one of the leading testing labs in the world. Okay, so the main background or the main basis to the company is it has a production side and an R&D side, and it works with a range of equipment. So what we can see in the picture here is some of the on-site, you got a clean room at the bottom there, a CNC machine, a large oven, and two, can't think of the word now, 2 autoclaves. So the brief overview. So there's the production sides. So in terms of wind turbine blades, Air Composites produces 13 meter and 14 meter turbines. So they're usually used for replacement blades for V27 and V29 turbine blades or turbines. They also produce polypropylene blades for SD Wind. So these are the ones that are used in the operational trials for the Leapwind project that I would have mentioned earlier. The main technology that is used for building the larger wind blades and also some tidal turbine blades recently in air composites is powder epoxy. So this allows you to do a kind of a two-cure production mechanism. So you produce all the parts individually at a lower temperature where they're solidified, and then they're essentially all put together, bagged and put into a large oven and then cured at a higher temperature for a final cure. So this, the main advantage of this is you can avoid glue lines and adhesives that would be a failure within the wind turbine blade. We've got some examples here of the blades after they've been produced, and the main advantages of powder epoxy. So it provides good fibre wet out, which is particularly a problem for carbon fibre reinforced epoxies and in all thick sections, which are essential for tidal and wind blades. There's reduction in post-processing requirements, reduction in material weight, and transport and storage costs. Some previous projects then that Air Composites worked on is the powder blade project, where they created the large manufacturer or the large parts that were being manufactured within that project. So it was a Horizon 2020 project in partnership with Westbic Suzlon, who were meant to talk on this call as well, and the University of Edinburgh. So the main focus was on blade roots and spars for 50 to 100 meter wind turbine blades. So a bit of background on the main objectives of powder blade was to design and manufacture a carbon fibre spar and a glass fibre root for a full-scale blade, which were built at Air Composites. There was also some work done on computation modelling. A full torsion box was built at the end and tested at the University of Edinburgh, and some of the work that was done in this project helped to reduce the cycle time for blade production. So here's just some of the examples of the computational models that were developed by James McGuire in the University of Edinburgh for thick section laminates. So for one of the first main big studies into that area. And here are some of the demonstrators that were built at Air Composites. So we've got a single section there. I think that's about 70 mil thick, which is quite thick. But recently Air Composites have built roots for tidal turbine blades that are over 130 mil thick, some of the thickest in the world. And it's the powder epoxy technology that allows that. There was also carbon fibre spars built during that project. And here we can see the torsion torsion box, which is a quite unique type of blade, because you've got a glass fibre root on it, and there's a transition period and a carbon fibre for the rest of the spar cap, spar cap and webs. So that this is real cutting edge and stuff that Air Composites were involved in. Some of the other research then, the Leapwind project, so I spoke about this earlier, and Air Composites are the lead of this project with Suzlon and ourselves at NUI Galway. The main manufacturer, and they produce the blades with the leading edge that were de-risked in the structural testing aspect, and now being deployed for operational trials. And the future of this project would be that it would see the technologies developed being commercialized by Air Composites for future wind turbine blades, so they can make more robust wind turbine blades, particularly for the offshore market. On a slightly different project, this is the Horizon 2020 SEAI project, where as part of the SME instrument, Air Composites are building a 8 meter yacht essentially, and this has been made from the powder epoxy technology as well. This will be a lightweight electrically powered boat when it's finished, but as you can see from these photos, it's well on its way and nearly there. This is just an overview of what's been going on in the marine energy and aerospace. So the blade on the top right here may look familiar from earlier in this seminar, where Jamie Goggins talked about the testing going on at NUIG. So this blade was built by Air Composites, one of the largest tidal turbine blades in the world, probably not the largest, but close to it, at 8 meters and weighs 4.4 tons. And the work that went into that and the manufacturing quality is probably second to none. And then down the bottom, we've got another example of a marine energy application. So the rotating components of the ORPC RivGen turbine were all manufactured by Air Composites, and these have been, what we see here is the deployment of their turbine in Alaska, where it provides electricity to a community that was previously relied on diesel power generators. Some of the other projects then is a Flowtech project, actually, where that falls under an air epoxy. So within this, they're a partner in it, where they're developing a novel epoxy-based composite for the aerospace industry. And there is some aspects in there where they're looking at leading edge erosion on planes. So I think that's it in a nutshell, and I hope I did the Air Composites justice. Any questions, I'll try and field them or redirect you to Thomas Flanagan, who's the CEO of Air Composites. Thank you.
Thank you very much, William, for standing in at short notice on that presentation. We're now going to engage in an experiment. Sandro Denoy of Sulson Energy Blades hasn't been able to present directly, but Julie Toiven has agreed to channel his or his sound via her setup. So we'll experiment with a presentation in that manner, and hopefully it will produce a reasonable sound quality. So thank you, Julie.
Yeah, let's try this out. Sandro, you're now unmuted.
Good afternoon, everyone. I hope that you can hear me properly. We are doing our best in order to, let's say, find a solution for this connection issue, and we will give it a try at least. And thanks a lot. In case of troubles, please let Julie know, and we will decide on the next steps. Okay. So today I'm here representing Suzlon, and within this presentation I will give a company general overview, and as well as some insight about also our part of the task within the Leapwind project. Now, Will, if you could go to slide number 2. The title should be Suzlon Company, some facts.
Yes.
Yeah, it's up there.
Suzlon is a company which was founded in 1995 with just 3 employees in a city in Gujarat in India. And at the moment we are running with above 7,000 employees globally, and we have installation in 18 countries. There was there was an acquisition of Repower, which became Sendion. Now Sendion has been bankrupted, and that was something that Suzlon was trying in order to enter the offshore market. At the moment, let's just say recently, we reached over 11,500 wind turbine globally, and with a cumulative installation of 17 gigawatts. We are the market leader in India in terms of installed capacity. The operations of our turbines are about several continents, and we have a full integrated supply chain, which means we are the company developing all the components which compose a wind turbine. So we are not buying blades from other possible suppliers. We do design and manufacturing our own blades. The last point is about the research centers, and we do have research centers in India, Germany, and the Netherlands, and that's exactly the research center which I belong to, and this research center is the one responsible for blades. Now, Will, if you could kindly go to slide number 3, please. It's a Suzlon company profile still, but simply with more schematic view of what I was explaining before. We do have the product portfolio here. There is an error because it stands at 2.3 megawatts, but we are already above 3 megawatts. And the trend will be maybe even higher from 3 to 3.3 megawatts in the near future for us. As I was telling you before, there is an integrated business model which englobes infrastructures, equipment supply, and services. Now, if you could go to the next one, please, let's talk a little bit more about the technology. Slide number 4, and our target as a member of an R&D regarding blades is to develop, design, and certify all the blades which belongs to Suzlon turbine models. In particular, how our technology organization works is based on 10 structured steps for the new product development process, design change process, and technical change instructions. And the most important part is that the R&D is also supporting all the other groups or departments, in particular the one in charge of product support for OMS, which means if there will be any particular problem about our products, we will be informed and we will cooperate with all the relevant departments in order to solve it. Now, number 5, it's the overview of all the existing R&D centers within Suzlon. There is one in Germany which are located in Hamburg and Rostock. And then, as I told you before, I'm belonging to the one in Hengelo for blade design and integration. And one of the most important points as a wind turbine manufacturer, and blades in particular, is the possibility to test our full-scale blade internally, and that's something which we do in Vadodara in our blade testing center facility. While in Aarhus, in Denmark, we do have a section of our R&D which is analyzing the SCADA data from all the wind turbine installed globally, all the wind turbines installed globally. Yes. Now, if we go to the next one, number 6, what I would like to explain with these few slides is that within the wind turbine industry, as it has been also clearly mentioned in the previous slide, the leading edge erosion is a real topic which we need to handle properly. Now, all the wind turbine manufacturers or blade manufacturers as well are working together in order to define a new recommended practice through the guidance of the NVGL in order to be able to really evaluate a leading edge protection product and how long that product will stay on our blades. Now, the challenge is still how to correlate the rain erosion test results to the real erosion on the blades, and that's something where several researchers, as I was watching today, are also involved, and that's the main challenge for the future. But having these recommended practice in place, the situation seems to be improving a lot. Even the possible leading edge protection suppliers are developing new products able to last more than before, even in the rain erosion test, and they are fully cooperating with us as possible customers to develop always a better product compared to the past. Now, within the Leapwind, as it was clearly mentioned in the previous presentation, the challenge is to be able to evaluate the thermoplastic leading edge protection. What we've done in Switzerland is that we were aiming for a real test on the real running blades, but as you can imagine, this part was planned to happen at the end of the project, which is the project will land in December 2020. So we were planning it in the last 6 to 8 months of the project, but unfortunately, as you can imagine, the corona pandemic, travel restrictions and country-specific restrictions did not allow us to perform this kind of test. For this reason, we decided to run a medium-scale test. So what we have done, we took a real tip of a blade that in this case, as you can see in the drawing, is a 63-meter blade. Out of that tip, we manufacture a mold, which is the first picture on the right. And then out of the mold, we are able to produce, if we move from right to left, the leading edge copy of a real 63-meter blade where we can perform all the possible medium scale application tests. Because as you can imagine, the evaluation of an LEP product in terms of chemical properties or rain erosion test is not done by us, but we rely on the information received from the suppliers. And at the same time, then we do send to the possible LEP suppliers our substrate information like filler for filler and top coat in order for them to perform an adhesion test, verifying if their materials are matching with our requirements about adhesion. Now, if you could kindly go to number 7, please. There are some pictures. So if we start from the top left, so we manufacture 2 leading edge copy of the 63-meter blade, and I mean, we needed 2 because in Switzerland we have 2 approved suppliers for filler and paint. And for this reason we manufacture 2 in order to verify how the Leapwind thermoplastic solution would work on both substrates. And as I told you, as a wind turbine manufacturer in blades in particular, we need to take care of all these small differences because the material could really degrade faster or the adhesion could be way less than planned, just jumping from one approved paint to another one. In the second picture from the left, from the top left, there is the application of the glue as designed by Aero Composites. Then there is the sparkling of the glue, and then if we go to the down left picture, then you can see the operators handling a piece of the thermoplastic LEP in order to place it on the laminate. And then the slide ends with the last picture, bottom right, where you can see already the application in place. Then if you could go to number 8, we can see the top left picture, which means the material is under vacuum for the curing. And then the last one on the right is the result of this experiment. Now, as a wind turbine manufacturer, we can say that we are really looking into the possible thermoplastic solution together with the project partners, because the thermoplastic solution will give us also the possibility to recycle the material easier than the other ones. And it seems also in terms of properties that the material is performing not that bad compared to the others. But from here to say that Susan is going to implement this material on our blades, that's a little bit more tricky, because all the products need always to be certified and so on. But together with the partners, we are at a very good stage, and we hope we can continue this cooperation in order to evaluate further this solution. And slide number 8, and then number 9 is the last one. And if there are any questions, please, Will or Julie. Now I'm going back to I can watch the presentation as an anonymous participant, so if there are any questions, please feel free to ask.
Thank you very much, Sandro, for an interesting presentation that complements the other presentations, and also thank you, Julie, for facilitating that. I'm afraid that we're running very close to our allotted time schedule, and while we have a lot of interesting questions, we're running out of time for the Q&As, and some of our participants have to depart. So I'd like, a lot of the questions that have been posed have been answered by the presenters in the Q&A, so you can our audience can refer to that. So with that, I'd like to thank all of our presenters and our hosts for the webinar, NUIG, for both excellent presentations and for the work into organizing this webinar. I believe it's given a view on the breadth of research that's been carried out in Ireland and the organisations that Ireland are also collaborating internationally. I'd particularly like to thank our international speakers today also for presenting. I suppose the one thing I would say was that it surprised me, particularly when we did put out a research call for research on leading edge erosion, that we had such a depth of expertise on this topic within Ireland. So it's certainly been useful to repurpose that expertise in the area of wind turbine blades, and I suppose to give us a foothold in that research sector. Just on other related announcements, SEAI's 2021 RD&D call will shortly be advertised, and anybody who's been inspired by these presentations and who has other potential projects on wind turbine blade research, certainly watch out for that call that will be advertised early in 2021. We've had a recent call for IEA Wind Task participants, and we've had quite a response to that. There are 3 new proposals for IEA Wind Tasks on airborne wind energy, on floating wind turbine arrays, and on hybrid power plants. So again, we'd be looking for participants in those. We have some existing participants, but there will be room for some more. So thank you all for participating and attending today's webinar, and again, thank you to all our presenters, and I hope it provides our audience with some new perspectives on the research on wind turbine blades across a variety of disciplines. So thank you very much, and goodbye, and stay safe.
Thanks very much, Sean.